Work done. So as we discussed in the previous class, in physics, we have a very specific way of defining work. Work is done, we say, when a force acts on an object and it produces a displacement in that object because of the force, obviously. And work done, therefore, is equal to the product of the force and the displacement that has been produced by the force. And we also say specifically that uh, work is done work done is defined as force, the product of force and displacement, and the displacement has to be in the direction of the force. Okay, so why talk about displacement and the direction of the force? Okay, so let us look at some situations to understand that concept. So I was talking about two situations, one in which there is a force that is being applied in this manner. So the red arrow indicates the force. So there are two situations. You can think of it as a box with a string tied and some person is kind of pulling that string in that direction. Okay, and another one in which the same situation is there. There's a box and a string, but the person, let's say, is sitting down and pulling the object towards himself or herself. Now the question is, will the two forces produce the same amount of displacement if applied for the same period of time? Now, somebody had already answered that question in the previous class, so I won't go back into it. The answer is that we don't think so. And why is it that you don't think so? They said that, look, because the force is acting at an angle to the horizontal, because of that, there is only one part of the force. If you take it as x direction is the horizontal one and the y direction is the vertical one, then the x component of the force is the one that is doing the pulling in this case, and that x component, F1x, is definitely going to be less than F1. What about the other part? There is a y component that is acting in the upward direction. We will come to that in a short period of shortly. Now, if you look at this situation, the force F1 is completely acting in this direction. So since F1x is definitely going to be less than F1, this situation for the same period of time will produce a greater displacement than this, right? So therefore, if you compare the work done in these two situations, so you can say that the work done in situation A will be F1x times d1, and the work done in B situation will be F1 times d1, sorry, d2. Okay, and since F1 is greater than F1x and d2 is greater than d1, we can say that the work done in situation B is going to be greater than the work done in situation A. All right, there are some implications to this in terms of sports and other things. I will come to that in a short while. Now, if that situation is clear, then we can move into looking at two more situations. Situation C. Situation C, we can say, is a dynamic situation. So far, we were kind of looking at static situations that become dynamic. But let us think of a dynamic situation in which there is a box and the box has a certain velocity. So it's moving in this direction. Okay, and if I apply a force on it in this direction, how do I do that? Well, it's kind of simple. Let's say I drop one of you from the top onto this box. So you land on this box.
Ouch.
Okay, and because you landed on the box, you're going to apply a downward force on the box. Ignore the friction for the time being. Okay, so the box has been moving, and on the moving box, you're dropped, like in a movie. Okay, now what is going to happen when that force is
Wait, the box was still when we dropped on it, right?
no, it's moving, it's dynamic.
Oh, so the box is moving in what direction? Okay.
Okay,
So it's
so
like the box is on the conveyor
let's say
belt.
it has a velocity in this direction.
Like the box is on a conveyor belt and it's.
Great. Yeah, that's a good one. It's on a conveyor belt moving at a uniform velocity and somebody got dropped on it. I mean, let's say like, in a baggage carousel in an airport, the bag was coming and you put another bag on top of that bag.
Okay.
Yeah.
Okay, something like that. What is the effect of the force? Or I can ask, will there be any work done on that object when this happens? Okay, so that's one situation. I'll add the second situation also. We can discuss these two situations one after the other. But the next situation is, and maybe this will actually give it away, the answer to this situation, if you think carefully. Same box, same movement. There is a certain velocity with which it is moving, and you apply a force in this direction. Okay, again the same question, will there be any work done on it? How can you say whether the work will be done on it or not? So in both the cases I am asking you, what is the work done in situation C and what is the work done in situation D? Are you able to see the work done in situation D?
Yeah.
Okay, great. So how will you answer these questions? I'll give you a couple of minutes to think about it, write down your notes and so on, and then we'll discuss the situation. So carrying on through the discussion, some people have expressed their opinion that they think there is no work being done in this situation. Okay, and the reason they said is, well, there is a force, all right, but there is no displacement in the direction of the force. The question that was asked was, well, is there any necessity that the displacement will have to be in the direction of the force? Why can't we say that why do we have to accept the statement that the displacement has to be in the direction of the force? Because this is a dynamic situation, and if you assume that either it's a baggage carousel and it's a conveyor belt, or there is frictionless surface, when you drop a person onto this object, there is going to be some displacement after that. The container will continue to move, right? The mysterious box will continue to move. So there is a force and there is a displacement. The only thing is that whether the force is along with the direction of displacement or not. And Ishan says, why should I accept that statement as being true? Very good point. Maybe we don't have to, but let us keep that for the time being. What we can see, however, is that the work done is maximum in this situation. The work done reduces a little bit because of the components breaking up in this situation. That is also obvious mathematically. Okay, here we are not so sure. I hope you are able to see what I am trying to do. And then I come to this situation. Maybe we can talk a little bit about this situation. So here also the object is moving, but now there is a force being applied in the opposite direction. Okay, like let's say that there's a very heavy object moving, so it has a lot of momentum, and you try to hold the object with a rope or a string. Okay, I don't know, has anybody tried stopping a running Labrador with its strap? It's like walking a dog and you're holding a leash backwards, if you can imagine that situation. Now you can ask the question, what about work done in this situation? Okay, what can you say?
I mean, the box is being stopped, right? So it would have gone to a different, it would have gone a certain distance if the force hadn't acted on it.
Yeah, but it
So
may.
the force is causing a difference in
Yeah, exactly. So you're saying that, look, the way I'm looking at it, if the force were not there, then it would have gone a certain distance. But if I applied a
Yeah.
force, then it would have gone a certain lesser distance than that.
There is a displacement in an indirect way.
There is a displacement in an indirect way. Exactly. So let us look at it now in terms of the equation. Okay, so let's say work done in situation D. Is there a force that is acting on it? Yeah, there is a force that is acting on it. That force is F1. What about the displacement that is there? There is a displacement, but the displacement is in a way indirect. Okay, but I can't write it like this. Why? Because this looks exactly like this. What are we forgetting?
With a minus.
Yes, exactly. So if you say that this is the positive direction of x and this is the positive direction of y, then this is the negative direction of x and this is the negative direction of y. Why we don't need to bother about at the moment, wink wink, nudge nudge. But if you look at it in terms of x, then if the displacement is in the positive direction, then the force is acting in the negative direction. And if that happens, then the work done turns out to be minus F1 times D. Okay.
So the C situation, the work is not being done. Is that been declared?
Why are you saying that? What prompted you to say that?
Wait.
Because
It is slightly.
One after the other, please. I thought Anadia was saying something.
I think there is a way the work can be done in the C situation.
Hmm.
It's like because there is way the full mass of a person is being added on top, right?
Hmm. Correct.
So
This weight
that is going
acting.
to slow the box down.
Yeah, it's going to push the box down further, but then there is going to be a normal reaction force that is going to act in the opposite direction. So will
But
there
it's
be?
also going to slow it down.
Huh?
It's going to slow the box down, right?
If it's on an
Why?
if it's on a conveyor belt, then it won't slow
How it's
down.
gonna slow?
Wait, yeah, that won't work. I was thinking of a different way.
In fact, a conveyor belt situation, it might just slow down because there is a motor that's applying a force. But if you think of it as a an object that is sliding along frictionlessly, right? Then it's very interesting. If you drop the object on top of it, if you are able to answer whether work is being done or not, you might well give the answer to a question that was asked at the end of last class. Somebody asked, what about satellites going around the earth, artificial satellites? In fact, then I can expand the question to say, what about the moon going around the earth, and what about the earth going around the sun? Okay, it's connected. There is something to be said over there, but I want to make a very simple connection. Okay, the connection is this: when F1 and displacement are both in the positive direction of x, then the work done is positive. When the force starts acting at an angle to the horizontal, then the work done reduces. That is also obvious. This situation, well, we are not clear right now, but in this situation, when the force is opposite to the direction of displacement, the work done becomes negative, from positive reducing to negative. So what could this be intuitively?
Yeah, in the middle comes zero.
Sorry?
In the middle comes 0.
Then in the middle one, there is a possibility that the work done in situation C is 0. Okay? And to understand this very clearly, we need a little bit of trigonometry because, okay, we don't need trigonometry. We have something better than that. What we have is vector geometry. Is there any component in this direction for this force in the x direction?
No.
No, x is 0.
X is 0. So if there is no force acting in the direction of the motion of the object, why should it affect the velocity of the object at all? From first law, as simple as that.
Yeah.
Get it?
Yeah.
Okay. So that is
No, but then it will affect the velocity, right? Because mass is being added.
Yeah, exactly. So there you have to forget about the fact that you need a force to be pushing this. Okay, if you were pushing this, Ishan, and then I drop somebody on top of it, then the mass increases, so obviously the acceleration will go down.
Yeah.
Right? So I'm not talking about that situation. This frictionlessly, it's just floating. I mean, it's just like sliding along the floor, and then if you drop the object, and I ask you this logically,
Yeah, we're ignoring friction.
is there any force acting in this horizontal direction, either this way or this way? No, because you cannot split this in any way because it's acting exactly downwards. Then there is no way in which there is a force external unbalanced force to change the state of motion of the object. So if you don't change the state of motion of the object, that means there is no displacement in that direction of the force. Therefore, the work done equals 0. Okay. So if you ask the connection, well, if this were not to be true, then we'd have artificial satellites crashing down on us. The moon will crash into the earth in a matter of hours, if not days, and the earth would spiral into the sun. Why I say that is because if you consider the situation of an artificial satellite going around the earth, are you able to see the connection?
Yeah.
Not right now.
Not right now, okay. Say there is an artificial satellite, okay. It's a gigantic, are you able to see the picture?
Yeah.
Yeah, yeah.
Okay. So this artificial satellite is going around an orbit. I'll just draw this much part of the orbit, okay. Now, what is the force that is acting on this satellite? What are the forces? It's in space, remember, so air friction and all these things just doesn't exist. What is the only force that is there?
Gravity.
Gravity, its own weight, right? So there is a force mg that's pulling it downwards. Let us assume that it is moving in this direction, okay. Now, the way satellites work is that they fall, but what is happening is since the earth's curvature is also going along with it, so they fall at a certain rate, they move at a certain rate.
Yeah.
That always keeps them at a mean distance away from the surface of the earth or the center of the earth, as you might want to consider. Now the thing is, the weight of the satellite, why doesn't it pull it closer towards the earth? Well, it doesn't pull it closer towards the earth because it's at a perpendicular to the tangent at that point. So the weight is acting like this, its displacement is in this direction. The displacement, see, its movement is tangential. Ink ran out. Tangential.
Yeah.
So when the force is at a tangent, when the force is 90 degrees to the direction of motion, 0 work is done. And that is the reason why the satellite will move no closer to the earth at any point of time. If it were not so, then the satellite would collapse very quickly onto the earth in a matter of minutes, so to say.
Oh.
But it moves, right?
Huh? Yeah, it moves, it continues to fall around it, around the earth. But at any point of time, its own weight will not drag it downwards as long as you make it move a certain rate. I think it's like 8 kilometers per second. Okay, do think about it. It's not very apparent, it's not very clear. A whole lot of concepts have gone in together. So you would have to carefully consider whatever arguments I have put across and see that it is logical, rational, connected, mathematically sensible, and so on. Another factor I would like you to look at is there is theta over here, which has a certain angle. Theta is 0 here. Okay, theta has some value over here, theta is 90 degrees here, and theta is 180 degrees over here. So if anybody is interested, just look at the values of cos theta. Cos theta is actually this component. Okay, so you look at
The
cos theta
forward
for
vector.
0 degrees, 90 degrees, and 180 degrees. You just punch it into your calculator and you will get the values. Then that will be a trigonometric explanation for why this is true, why this holds true. Thank you for watching that video. I hope you liked, understood, and were able to appreciate what we had discussed. If you like that video, do click the like button, consider subscribing to my channel, and do leave your comments about whichever aspect of the video you had any questions about or appreciated, and whatever else you would like me to put as content on this channel. Thank you. See you until next time.